Hey, how's it going? Today we're doing educational round 134. Um, About to get started, and here we go. So let's see, 6 problems, cool. 4 pixels. Choose more than 2 that are the same and paint them some other color. I mean, I think you just count how many colors there are, and then it's colors minus 1. So, whoa. Unique. I think it's just right. Yeah, so we don't have very fast splits. I think that's just right. Cool. Keep going. N rows and M columns. So M print -1. Oh, you have to avoid the laser. So there's some diamond that is not allowed. Interesting. Wait, what? It seems kind of... But you want to go from 1, 1 to NM. Oh, so I think you should either go that, the most extreme path. And I can do N plus M, that's fine. So what am I really checking? I'm really checking if I'm really checking if it's close enough to... I think I can do this in constant time, actually. So this is going to be... I don't need abs. And M minus SY. Let's go to D. This is going to be N minus X squared to D and SY minus 1 to D. Top okay or bottom okay. If that's the case, then it's M plus M minus 2 is M. Okay, let's do it. Looks like I'm a little slow today, but that's okay. Alright, problem C, min-max and rate transformation. And BI equals AI plus DI for each BI. Sort the BI. Okay. We're given AI and BI. Okay, so yeah, it's like how extreme. I see. DI has to be non-negative. DI has to be non-negative. DI has to be non-negative. Aha. Okay. Okay, I see what's going on. G. I'm just gonna. Alright, too many typos. There's one way. So clearly BI is at least AI, because if that's not the case, then if BI is less than AI, then there's not enough numbers to match up with AI for AI. So if you want to match like A3 with B1, well then, no, that's fine. Yeah, that's easy. Minimum is easy, I think. You just find your lower bound and then you can do this. This is totally fine because so it has to be the case. Okay, and then minimum, you know that minimum, the worst minimum, okay, so minimum is just easy. It's just going to be lower bound. It's actually pre-and AI. I'm going to take it and subtract AI. So I think we can test this. That should be the minimums. 542, 4,000. Okay, now maximum. Maximum is a little tricky. So maximum is like this. Well, we need to know how long it's okay to be one lower. Okay, so you just combine both those things. It's just going to be AI less equals to BI minus 1, right? And then you want to know how long is that okay? How long? I actually have to go backwards. How long I equals otherwise it's just 0. So maximum is just going to be this. Just 1 is okay. Is a B I plus how long I. Sorry, how long I plus 1? Yes. Minus AI. I think that is right. Okay. Oh, all my timing is really bad. Okay, so am I sure that this is not going to go over because it is at most enough to get to n. N minus x 1. Yeah, so yeah, this is, I think this is fine. This, I could have written this in linear, but whatever, it doesn't matter. Cool. Wow, third place. Not too good. Alright, keep going. The maximum and. Two already solved. But they're not on the leaderboard, interesting. FAB. Yeah, XOR BI. And then and everything. Oh, we can reorder B. We can reorder B if we want the and of the X scores. Oh, yeah. Don't you just go bit by bit? We go bit by bit. You're like, can I set this bit to 1? How do I set this bit to 1? I need to... Well, if I can reorder B anywhere I want, I can also reorder A anywhere I want. So, yeah, let's do that. Okay, it's just... The total number of ones across both arrays in that bit is n. And then we have to... Ooh, now we have to coordinate together. So you have to set that like that. You have to coordinate together. There's a point where you want to begin. That's fine. You just keep your groups and you just do it. I think that's fine. I can't type today. So you have groups. Group is, it's 2 vectors. Groups. All is it? I really shouldn't call this all. All, it's called like everything. Okay, so, and then groups equals everything. It's 1 entry. Now for bit, because it's less. Okay, yep. Then we're gonna check every group. Full code equals true for auto G in groups. I'll call this group. If check group bit or really it should be split group. I need to figure out this returns. I mean, it's your turn 2 groups. It returns 2 of these. Okay. So it's the yes, and then they have to be the same, and then ones plus equals a group 0I 1, and then also b group 1I. If 1's not equal to n, return what? Excess elements. What? Is this better? What does it want? Oh, I'll just make this a vector. I'll just make this a vector. And I'm just going to turn empty. And not dot empty. Great. Okay. Problem solved. It's really weird. If there is a way, you're going to have the zeros, the A zeros, and then the A with the B1s, and the A1s with the B zeros. So we're going to have 2 of these. 2 new group 2. If a group 0I shifted to n1, actually we're just going to do that. N group 0 got pushback group 0I, and group B group 1I shifted to n1 1 dot pushback group 1I. That's it. Let me turn this. Okay, if not good, continue. Otherwise, we need to redo our groups. New groups. For auto group and groups. Split group, and bit. N groups dot insert and groups dot n begin n group. Groups dot swap and groups and 0. Okay, I think we did it. That was sort of. Oof. Okay, let's see what happened here. hint. What's wrong with this? I hoop 0 size. I did 1 dot size. Why do they match? They don't match. Oh. This needs to be the opposite. This is the opposite. Oh, that's kind of tricky. Okay, I think we got it. Oh, it's 20 minutes in. That's not good. Wow. We have E. What? Is this TLE or something? No, it can't be, right? How is this TLE? This is... Oh, this is really annoying. Random gen. 100,000, 0, what is this now? I really should have just know that. No, yes, no, creative. Oh, excuse me. Alright, and now we're gonna append. Now we're gonna do that, and now we're gonna do that. It's very fast. Oh, it doesn't do anything. But what? How can this be too slow? This part is O of n. This whole part is O of n. Oh. Ah. Is that why you can just end up with tons of empty groups? I think that's why. That's... Oh, and that will work, and that will give you 2 new groups, and it will just keep exponentially expanding. I see. Okay. Okay. Oh, that's kind of a lot of runtime. No, that's not good. Alright, did I get... No, I got 10 penalty. I should have been here. Alright, keep going. Prefix function queries. Everything's been solved. Lots of memory. Okay, makes sense. String S, no case letters. Concatenate. Prefix function. Maximum value k such that k is less than I is just camp p. Proper prefix that is also a suffix. Oh. Oh, we're given a bunch of short strings. We want the failure function on those prefixes. I need some water. You're saying we have a long string and then we have a short string on top of it. And is this better? Oh yeah, this is better. This is way better because you don't have to do right. Because the original camp here relies on like this, which is amortized, but that's not good. Okay, so now we're just gonna. I don't know if I exactly want this code. Well, G. Okay, so what's to do? Why can't I? Oh, is that because it's set here? Yeah. Okay, so. Sure. Oh, no cases. Template. Probably for X. So that looks like a long problem. All right, now let's pair this. Lowercase, yep. So link is going to be compute link on S. Wait. What is link? What does that do? It's if you have this prefix and then you take this character, how long is your match? I think. Yeah, I think you can just do. Well, how do you get the failure function from the link? kind of just doing this code. What is TMP max? No, L max. But it's going to be you take link IC, right? I think fail I plus 1 equals link IC. What? Suddenly it's 6. So a 4 5 4 5. Is this the right way to compute the Taylor function? Oh, what? Huh. That's very weird. Otherwise it's the same. I'm confused though. You know, I don't need Lmax, right? It does match, but it just doesn't. Here it's gonna fail, right? But it doesn't fail here, it fails here. It's very strange. It's very strange. Because I'm just continuing the algorithm here. What is the difference? What is even the difference? 00014545. Where did that come from? Where did that come from? S dot resize n. Does this affect anything? No, it should not. It really should not. I don't understand. But it did. It apparently got different values. Something weird is happening. Something very weird is happening. Resize. Do I not understand what this is? If we pretend it was just s plus t in the first place, then we're going to do link, we're going to do fail, it's going to have these sizes, and then we're just going to keep going, yeah. 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 This is literally a copy paste of this. Link I plus 1 equals link previous. Oh, we are messing up. Okay, save link. Oh. Ugh, that's so silly. Is this it? That's it. I think that's it. Okay. Alright, so I'm gonna get rid of all this. Get rid of all this. Get rid of this. Get rid of all this. I should have done that way faster, way faster. It's so bad. No, no, come on. Who wrote this problem? I can't have... It's only 26 million hits. I need to reserve. I need to reserve. Okay, so... link.reserve. Even if I could double that, why is it... What? What is happening? It's this constant resizing that is messing it up? I think this is fine. Okay. I'm getting very annoyed now. Why am I MLE? That's the dumbest way to fail. Why does it use so much? What? Wait, what if I just do this? Oh, we also have to move this. I just don't understand how I got Emily. That's insane. It's insane that I got Emily. It's insane. Oh. Well, I have one of the fastest, I guess. Okay. That's frustrating. All this extra penalty. Okay, time for F. Matching reduction, 8 seconds. Bipartite graph. N1 vertices and N2 vertices and N edges. remove the minimum. What? What? You have to print. Oh, you just repeatedly reduce it. Some indices that just belong to this matching. Right, and you have to have it ready at any time. Okay, this looks like a tricky one. This is clearly the hard problem. Hello? People have solved it. Oh, wow. I just obliterated one. His penalty is better than my penalty on 5 problems. 25 minutes, huh? Let's see about this. So, to remove, well, by Koenig's, max matching equals what? Min vertex cover? Oops. I didn't search that. Alright. They're just equal. So we can just think about, oh, we still have to find the matching. Let's count that. Oh, but you just remove a vertex from the main vertex cover. No, not exactly. Well, oh, yeah, that removes all the edges. Yeah, wait a second. This is a matching and just... I mean, if you remove one of the vertices, you decrease the min vertex cover. Because you got rid of all the edges that it's like you use it. So yeah, you can just remove one at a time. The only thing is, how does that affect? We're just doing incremental. Yeah, so you can just decide to. Yeah, each vertex cover endpoint is one end of the map. This is just really basic. I'm confused. I kind of think it is though. I kind of think it is. So I don't want this. Hint NME. I'm renaming this. I don't like their naming scheme. Yes, this is what I want. I can find them in vertex cover from this. And yeah, you can also see the matching. So, why did I do that? Okay, I don't know why I did that. Genetic matching, graph, and M. Graph, as usual, decrement, and then graph.edge x, y. Actually, no. The matching is... I can use the left match and right match. And then vertex cover. Yes. Yeah, so I'm just gonna read the queries. Oh, Q. I didn't read Q. Oh, the indices. That's annoying. I can, yeah, I can do this. Okay, so edges E. Sorry, not EI, I guess. Okay. Now we're gonna look up all these. I'll just use a map. Edge to index. Great. Okay. Int edge sum equals 0. M. If graph.rightMatch I is greater than 0, then edge sum plus equals edge index I graph.match I. Right match is what I think it is, right? It is resized. Yes, it's size n. And I'm going to assert int vertex cover size is match. And then I'm going to type cn type. If type equals 1. Else if type equals 2. Else assert false. Vector bool deleted n plus n false. Okay, now it is time to delete the... We're going to delete. It's 2 delete equals vertex cover vc plus plus. And I'm just going to call this v. If v is less than n, else. If u is less than n, and v, else v equals u, and then u is going to be graph.leftMatch v minus n. V equals graph.rightMatch u. So now we have a uv pair, u and v. So u minus n. Okay, so u and v. U and v. v becomes u minus n, because we're gonna, yes, and then left match, yes. So now, edge sum minus equals edge index uv, see out edge sum n del. Oh, I need to, no, output, number of vertices I remove, see out 1, see out, oh shit. Oh, this is weird. I'll see out negative u plus minus n plus 1. U minus n plus 1 negative. That is really, I don't like that, but what am I going to do? Okay, now I need to... I'm setting sleep. Alright, now, here's what I do. Indices of the edges. Okay, so if not deleted I and graph.right match I equals 0 and not deleted n plus graph.right match I, we're going to see out if space see out space equals true, see out edge index I graph.right match I. 3, 4, 5, 2, 1, 3, 2, 1, 3, 4, 2, 1. So what does it have? 1, 2, 3, 1, 2, 3, 4. We have 2 to 2, we have 1 to 3, we have 2 to 1, we have 3 to 4. So first, we're going to move 1, which is we're going to remove 1, and then the edge sum is 3. Okay, 2, so what? Oh my god, what? One, 1, 3, and then 2, it's going to be 1 and 4. That is not correct because, this problem. Alright, let's just do this again. 1, 1, 5. 2, it is edge 1 and edge 4, which is 2, 2, and 3, 4. I'll do 1 again. 1, 2. We remove the node 2. Okay, I think we're good. Let's just do it. That was very easy. Oh. I did decently well. Just was so slow. I just messed up these problems. Oh wow, there's a lot of penalty. Okay, I'm actually in a pretty good spot because I don't think 65. Like, these people can only pass me for a little bit longer. Cool. Bad gateway. It's just conics theorem, that's it. That's all you have to do. Alright, I'll talk about solutions quickly, and then I'll go eat something because I'm hungry. But, what do we have here? Let's see. Alright, problem A. You have a 2x2 grid, 4 pixels. They have different colors, but you have this operation. Choose up to 2 pixels of the same color and paint them some other color. And you want to make the minimum number of moves to make them all in the same color. So, this one, basically, the claim is you can treat it, you can just ignore this at most 2 pixels constraint. Why can you ignore it? Well, if you pick 3 pixels that are the same, then there's 3 A's and 1 B, something like that. So instead of picking the 3 A's and turning them to B, you can instead pick the B and turn it to A. And also if you pick 4 pixels, that's dumb because then you don't need to do it. So you can ignore this constraint of at most 2, and then just paint however you want to, as long as you just change one color to another color. And then obviously the answer is number of colors minus 1. So that's what we do here. I guess instead of sort and unique, this would have been shorter if I had done set char, combine, begin, combined, that size, and that's one. That is also fine. We can submit that just for fun. Yeah, so that's fun. I didn't even test it. That's good. Yeah, that's pretty fast. Alright. Problem B. Deadly laser. Alright, so basically you're at 1, 1 in the grid. And you need to get to like NM in the grid. And there's some point that's bad here. It's bad, and then there's some range D that's also bad. So maybe it's like, let's say D is like 2. Oh no, it's going to delete tabs. And you want to know, is there some path from here to here that doesn't touch any of these x's? And if so, what is the shortest path? So basically, my claim is we only need to consider 2 paths. One path is like this. Oh boy. All right, we have a lot of characters to add here with the ASCII art. One path is like this, the other path is like this. Oh. Wait, oh no, it's gonna delete like a lot more than one. Oh no. It deletes a tab. Okay, if I do this, it seems fun. Yeah, the other path is to go down and then go right. Those are the most extreme paths in these different directions. And basically, the point is, if both paths are invalid, then there's no way to get from here to here, because there is an invalid cut, essentially, from somewhere here to, say, somewhere here, or maybe to somewhere here. Anyway, the point is there's some line completely obstructing any possible path you could take. That it either goes top to bottom, or it goes left to top, or it goes left to right, bottom to right. It cuts off all possible paths because you would have to go through this. So if both of these are impossible, then it's impossible. And if either of these is possible, then you just take that path, and it is clearly also the shortest path. So it's really just a question of, is it possible? And that's just a question of, basically, is the top path okay? And all that takes is just, is this far enough from here and from here? And then is the bottom path okay? Is this far enough from here and from here? Just check both of those. If either the top or the bottom is okay, The answer is n minus 1 plus n minus 1, which is n plus n minus 2. Otherwise, it's not possible. So that's B. I'll save my beautiful drawing. And now we look at C. Yes, C was about taking array A, adding a bunch of non-negative integers to each one, and then taking that as B, and then sorting. So we want to figure out the minimum and maximum D for each position. So the main idea here is we can solve minimum and maximum separately. Now, first of all, the D have to be non-negative, and they guarantee you that the way that they did it, there is a way to choose the B, so it has to be possible. So the first claim is that AI is less than or equal to BI. Why is this true? Well, let's say AI is not less than or equal to BI. So in particular, AI is greater than BI. Let's say A3 is greater than B3. Well, in that case, we need to assign the BIs to the AIs in some order. And obviously, the assigned BI has to be at least this AI it's assigned to. And if A3 is greater than B3, then we have a problem because we have three values, A3, A4, A5, that are big, and then at most two B values that are big enough for them. So we cannot assign. So that means AI is less than or equal to BI. Now, in order to compute the minimum, well, first of all, once we have this condition, we know it's possible. We can always assign AI to BI, and then we're good. So that gives us like one option as a minimum or a maximum. So now to compute the minimum, we only have to consider for A3. Yeah, for A3, could we use B1 or B2? And for this, it's actually quite simple. You just find the smallest BI that is still greater than or equal to the AI. The reason is, let's say I assign A3 and B1, right? If I assign A3 and B1, and that pair works, and after that, you'll notice that A1 gets assigned to B2, which is fine because A1 is less than or equal to B1, which is less than or equal to B2. A2 gets assigned to B3, which is also fine for the same reason. A4 gets assigned to B4, which we already determined was fine. The main idea here is we need to make the assignments so that the BIs are at least the AIs. Same thing with A5. So we can just figure this out independently of the other AI. It's really just what is the smallest BI that is at least our AI. So I use binary search for this. You don't have to use binary search. You can just do this with two-pointer sweep. And I will rewrite it to do that just for fun. So basically, while B index is, maybe I will name it this so I don't have to deal with that. While B index is less than n minus 1, and B index plus 1 is, B index is less than AI, B index plus. And now int minimum equals B index. I can't type. All right, now this is linear time. And I'll just submit this for fun, because why not? So that is solving the minimums. Is it actually faster? It was slower. That's pretty funny. Now to solve the maximums. Now we want to know, can we assign A3 to B5, for example? So for sure, A3 and B5 is a fine pair. The problem that occurs is, well, these are all fine, A1, A2, and so on. The problem that occurs is now you have A4 paired with B3, which we don't know for a fact that B3 is at least A4, and you have B4 paired with A5, which also we don't know for a fact. So we kind of need to know, we have these pairings that go like diagonally down and left, A4, B3, A5, B4. You need to know how far we can do this before it's not okay. So that's what I compute here. I'm just computing, hey, is this one okay? This one okay is just AI less than or equal to BI minus 1. And then how long is it okay for? So I'm computing for each point, how far can I go right until it's no longer okay? And that's just another quick computation. If the current was okay, then it's the next one plus 1, otherwise it's 0. Yeah, and so then I just take that index and just, you need to be a little bit careful about the indexing here, but ends up working out. And that gives you the maximum. It's basically just literally until, you know, for example, if A4 is less than or equal to B3, and A5 is less than or equal to B4, but A6 is not less than or equal to B5, then the first thing you can go is you can assign A3 to B5. So that's the idea here. That is C. And cool, let's keep on going. Problem D, maximum and. So we have two arrays A and B, n integers each. Let's see what happened with the standings. Okay, it looks like we are cleanly in third place. Because, yeah, now anyone solving a problem would get 75 minutes of penalty, and yeah, that's too much. Cool. Anyway, back to it. Problem D. We're going to take an array C of size n, where Ci equals Ai XOR Bi, and then we're going to take the value of the and of all the Ci's. Now we want to find the maximum value of the function if we can reorder B arbitrarily. Now, first of all, if we can reorder B arbitrarily, we might as well reorder A arbitrarily too. So we can just reorder them however we want. And it's at most 2 to the 30 minus 1. So 30 different bits to consider. So the way that I thought about this is, first of all, we should just solve this bit by bit from high to low. If we can turn on, the biggest bit, we should do it at all costs. If we can't, then we just move on. So what does it take to turn on a certain bit? Well, in particular, you're going to need all these XOR pairs to get a 1 in the bit. That means one of AI and BI has a 1 in the bit, and one of them has a 0. So we need to pair 1s from A with 0s from B, and vice versa. So what exactly does that mean? That means across all the A's and the B's, the number of 1s in that bit is n. If that's the case, then we're good, because we just pair the A1s with the B0s and the A0s with the B1s. And it works out. For example, if this is the A and this is the B, we just reorder them so that, oh no, I have them locked on. We just rearrange them so that like this, and then the XORs in that bit are just going to be all 1s. So it's just total number of 1s is equal to n. So yeah, we find the highest bit where we can first satisfy this. Once you do that, that bit is on. And we need to continue down, but permanently keep that bit on. And then the way we do that is now, when we have that bit on, the A1s have to map to the B0s, and the A0s have to map to the B1s, right? So now we can have, we sort of broke the array into two separate problems, or two separate, groups. And that's just what my code does. I just keep track of all the groups, and now we have to do them independently. And now, if we have groups and we want to satisfy a new bit, the bit condition of total number of 1s equals n, or in this case, total number of 1s equals the size of the group, has to hold for every group. So the rest of this is just implementation, dealing with tracking the groups, checking if we can split all the groups, and then if we can, just doing it. And then there's this tricky thing that I screwed up here, where if you don't check for empty groups and throw them out, you can end up with exponentially blowing up of lots and lots of empty groups. Because this function takes a group, splits into two groups. So when you have an empty group, it'll always split it into two groups over and over, and you'll just get 2 to the bits. But yeah, otherwise, just a bunch of implementation. Key idea here is just thinking about what this means, and then thinking about how to handle the bits as independently as possible. Cool. Let's go to problem E. Problem E is basically asking you to compute CAMP. If you don't already know CAMP, then it's going to be a hard problem to solve. But basically, we have this big ass string S, and we need to compute CAMP for S plus T for a bunch of different strings T. The T strings are all small. So there's actually 2 ways to write CAMP. There's one which looks like this, where you just compute the failure function, which is what they're looking for, and you use this while loop, and it works in linear time because of the amortized analysis. This is not something we can just do here, because when we add these 10 characters, we could end up using this to fall back quite a lot. And our amortization could fail because we are not necessarily, we're kind of repeating the same operations. So we no longer have the same usual amortization guarantees. But there's this other way you can write it, which involves arrays sized by the alphabet. And the nice thing about this, even though it's worse in memory usage and time complexity has an extra 26 factor, it doesn't have any amortized time complexity. It doesn't have any while loops. It's just a simple 26 operation every time. And we can actually use this to compute the failure function. That is what I do here, because the failure function is here. And that is essentially how I handle this. So I've already pre-computed this for the original string, and now I can just go forward. There's no amortization involved here. I literally just copy-pasted this code. I just continue the algorithm just on these different indices, and then output the answer. And then this is a little tricky. This is what I tripped up on, because link I here can be link n, and then I overwrote that value, and that needs to stay preserved for the next query, so I just reset. All right, lastly, problem F. Problem F involves finding a maximum matching and then gradually reducing it one by one at a time, and then, if necessary, printing the edges that we need. This problem is entirely Koenig's theorem. Koenig's theorem says that in a bipartite graph, the size of the maximum matching equals the size of the main vertex cover. Yeah, and let's see, is there something that I skipped logically here? There should be a corollary here. There should also be a corollary here that the minimum vertex cover contains one end of every edge in any max matching. Or is that true for any, or at least for one? I might have to think of this for a second. So okay, so certainly if you have any max matching, then for every edge in the matching, at least one of its vertices is in the min vertex cover. Why? Because for any edge in the graph, at least one of its vertices is in the min vertex cover. So that is true. Now, if we have a matching, and we have a matching where both vertices are in the min vertex cover, then we kind of messed up. Like that messes up the theorem, because then we have to make up for it, we have to have an edge where neither one is in the min vertex cover, so that doesn't work. So, okay, yeah, this is just true. If you take any max matching, then for that matching, for every edge, exactly one of its two vertices is in the min vertex cover. Yeah, I'm pretty sure I just figured this out and then I forgot what I figured out. Anyway, that makes this problem really simple, because now we have the max matching, and we can find the min vertex cover, and we can just remove the vertex cover vertices one vertex at a time. Why is that okay? Well, if we take the min vertex cover and we remove a vertex that's in the vertex cover, let's say this one, then the min vertex cover after that just becomes -1. Why? Because removing a vertex from the graph is like adding it to the min vertex cover. It's the same thing. So we know that the min vertex cover will behave in the manner that we want, and because of this theorem, the max matching is equal to the min vertex cover, so that will also decrement by 1 every time like we want. So this becomes really simple. You just find the matching, you find the min vertex cover, they're the same size, and then every time you delete, you just delete from the vertex cover, and you delete the edge that corresponds to it. And this is just me handling the output format, this is me finding the edge, this is me subtracting. Yeah, that's pretty much it. And then if you just need to output, you can just iterate over all the edges, check if it's not deleted yet, and then print it. That's it. That's F. Yes. I didn't like that I had a map, because that is very slow. Edge to connect. I mean, what else can I do? I mean, I can use a hash map, I guess. Sure, let's do it, just for fun. Because this one was a little bit slow. We can make it faster. This one was pretty fast, so it's fine. This was annoying, though. This was very annoying. I guess it ended up not mattering, because even if I had... Well, if I'd saved both of these, I would probably have been second. That's alright. Yeah, let's try to swap this out for a hash table. Whatever, that's fine. Why is random address not needed? I use it right here. Very strange. Okay, so does it not complain on this one? It doesn't. Strange. Right. GP hash table. It's a little bit annoying, isn't it? Safe array hash is what I need. What? What is wrong? Oh, yeah. Well, Clang doesn't have this. What? Debug compile errors, but optimize compile succeeds? No. Really? That is bizarre. Did I put this too high or something? What is wrong? What is wrong with this? I could just put this here. I could just put this here. It's still... What? That is bizarre. That is very bizarre. Where do I use operator less? This? Okay. That's bizarre. Should be faster. Yep, a lot faster. Oh, nice, I have the fastest one. That is weird. Alright, I'll figure that out later. But cool. Thanks for tuning in. That was Educational Round 134. Hope you liked it. Feel free to subscribe if you want to check out my future videos. But Either way, I'll see you in the next one.